Hey, what's up, you guys? It's Issa with Journey to Programming. Today, I want to do a data structures tutorial on stacks and queues. I may split this video up into two separate videos depending on how long it runs, but we'll kind of see how that works out towards the end of this video. And if it runs too long, I'll let you guys know, and I'll just link you guys both videos and post them at the same time so you guys don't have to wait for it. So in the past, I've done a linked list tutorial and a lists tutorial specific to C Sharp. I'm also going to focus on C Sharp in this video. And yeah, let's go ahead and jump right in. So before I move over to the IDE, and I'm using Visual Studio today, let's really quickly talk about stacks and queues. So what are stacks and what are queues in terms of data structures? So really what they are is they're basically a method for accessing and adding data to a container or a data structure, all right? A stack works or behaves in a last in, first out kind of functionality. So the last item you add onto a stack is the first thing that will come out of it. All right. And an example of that would be a dish stack at a dining hall or something like that, or at a restaurant. And you can kind of visualize it as, let's say, plates in a rack sitting on top of each other. Usually you add the plates on top of each other into that dish stack, and the entire dish stack will lower. And when you're removing plates out of that, you pick a plate off the top in order to get to the plates underneath. All right, so you have to remove the objects from the top of the stack, but then whenever you add to the stack, they go on top, pushing everything underneath it down below. Another example would be a Pez dispenser with candy, right? So the way a Pez dispenser works is you load the Pez into it, and theoretically you don't have to load the Pez from the top and push it down. You could just open the entire thing, pull it from the bottom, and put the entire row of candy in there. But if you do load a Pez dispenser one by one, like some of us did when we used to play with those or eat that candy, then you put them in the top, push it down, and load them from the top down, right? And when you remove them, they come from basically the top out. And yeah, I hope that's a simple enough kind of example. So a queue, on the other hand, a queuing system is the first thing to get into the queue is the first thing to get out. So if you're the first person in line, then you're the first person to win or get whatever you're waiting for, or you're the first person out of the line. All right. So think about whether or not you're maybe really psyched or stoked about a new product. Maybe you're into Jordans. Maybe you're into buying the flagship new flashy iOS phone or something like that, an Apple phone or whatever the hip thing is, right? So you get there at like midnight, or you get there 2 days before and you camp out, and you're the first person in line. Since you're the first person in line, you're the first person to get out of the line. You get your product and you get to get out of there, right? If you were, if you had to wait in a stack on the opposite hand, then you would be, if you were the first person there, you would be the last person to get your product or the last person to get out of the line. So that would suck, right? So each one has its use case. There are reasons you're going to use them, especially if you're trying to traverse like graphs, or you want to figure out on like a map or a graph system what the nearest neighbor is, or if you want to maybe find a destination that's multiple endpoints deep, like a DepthFirst search versus like the breadth-first search, then you would use either a queue or a stack depending on what you're trying to do. All right, and we can dig into that later. I'll probably do a BFS versus a DFS search tutorial as well, because I think that's really helpful in understanding. Maybe I won't write the code for you guys, because I think that's one which is really helpful to work and grind through on your own. And if you learn how to create a queue and a stack and you learn how they function, then you'll definitely be able to create that once you understand how trees and graphs work, okay? All right, let's go ahead and jump right in. Let me move over to Visual Studio so you don't have to kind of just look at me while I'm doing this. And let's go ahead and begin by creating our stack, okay? So you could always use the library implementation of a stack that is contained within System Collections generic. So we could always utilize that, and in most cases, you probably will use the library version. You're probably not going to create this from scratch. There isn't necessarily a reason to make it from scratch or recreate the wheel unless there's maybe a really custom structure that you cannot fit into your use case, or your use case requires like a really custom stack or queue system that doesn't fit in with the library implementations, and you can't override the functions. So in most cases, you just use the generic implementation, but it's still good to know how to create it from the bottom up, just for your own knowledge, just for your education, all right? So knowing the inner workings will help. But let's go ahead and jump on in. So let's make a public class, and I'm just going to make it a stack, all right? I'm not going to go crazy. And this shouldn't have any conflicts with system collections generic, and just in case it wants to have an issue, I could remove that, but there shouldn't be a problem because this exists within my namespace data structures, okay? Now, let's go ahead and do a quick visualization of this. It's not the cleanest, it's not going to be all pretty on a whiteboard, but I think this will do. So what I'm going to do is I'm going to create a comment stack here, right? And what I want to do is I'm going to add in, let's say, integers onto my imaginary stack, all right? So here's my stack, and right now it's empty, okay? So let's just imagine this is my stack underneath it, and right now it's completely empty. Now I'm going to go ahead and add an integer into this. I'm going to add the number 5. All right, so now my stack contains a single value in it, or a single object, and that's the number 5. If I want to remove something, I could just go ahead and remove the top element, which in this case is going to be 5. Now, if I want to add something, let's say I want to add the number 8. What will happen is that number will add on top of the last object that was in there. So as you noticed, when I added it, the 5 is sitting below it. It moved down visually, and now the 8 is on top. So remember, you're always taking data out of the top of the stack or the front of the stack, right? So now if I want to add another digit, what do we think is going to happen? It's going to sit on top of the last value which we entered, which was 8. So let's add maybe the number 1. We've added 1 to the top. Now let's add a few other numbers. Oops. Let's say maybe 4. Nope. And maybe 13. Okay, so what we've done is we've added 5 integers to our stack here. And what I want to explain is how this data access is going to work. Because remember, this is a last in, first out structure, right? So the last digit that we added to the stack, which is 13, is the digit that will come off it if we try to remove something from the stack, all right? So let's go ahead and play with a little bit of logic. If we wanted to access the number 8 in the stack, we could not technically, if we're still following the way a stack works, we should not be able to access and just retrieve this value out of that stack. All right, that would not be the native functionality of a stack. What we would have to do is we would have to tell the stack that we want to remove 1, 2, 3 elements, and then, so we've removed 3 elements, then the top value or the top object is now 8. That next time we call a remove from our stack, it would allow us to get that 8 that we want, all right? So that is how that would work. Now, I'm going to really quickly segue over to what are the actual method calls here that we should expect to use. So if you've used stacks or queues before, then you're going to know these. So usually we have an add function. So that add function is usually a push call. So imagine you're pushing the plates down or you're pushing an object on top of the stack. The remove, let me go ahead and make this a little more clear. The remove is usually a pop. All right. So you're popping an object off the top of a stack. That's going to be the remove. And it's only one at a time. So before I add anything else, let's quickly think about this. So the very first time we added the 5, what we actually did is we called a push and we passed in an object or a value here, depending on how our structure handled an add method or a push method. All right. So this is what our first call did. And then we did a push of 8, a push of 1, a push 4, and a push 13. Now, in that last example, what I asked you guys to do is, how would I get the number 8 out of the stack? What you'd have to do is you'd have to call pop 3 times to remove these values. So you'd say pop, and then that would remove the 13. You'd say pop, that'd remove 4. You'd say pop and remove 1. So that's 3 calls you made. 3. Now the top element in that stack or top object is number 8, or the value we want. If I call pop once more, it's going to remove that value from the stack for us. All right. Now, let's go ahead and show you guys how to implement this. There aren't going to be a lot of cases where you want to access something like that. You're not going to use a stack in a case where you want to be able to randomly access data from the various kind of spaces within it, okay? It's more so going to be utilized when you want to reverse data, right? Because the way it goes in, it comes out in reverse. So if you have a data set, you put it into a stack, it comes out in reverse. So that's usually where you're going to use this type of structure. Again, it works really well for doing graph searches. So just a heads up. If you want to do a depth-first search, I believe, you'd be using a stack. Let me think about that really quickly. I don't want to give you guys the wrong info, but just thinking about a depth-first search. So what you're going to do is you're going to go to your nearest neighbor. You'll add those onto our stack. And then once you've added your nearest, so your like N1s, then you're going to dive into those N1s one at a time and go as deep as you can. And that's going to find its N1s. Yep, so you'd use a stack. If you do a breadth-first search, you're going to search the first neighbors and search all of those. You're going to exhaust your 1-off neighbors. Then you'll go to the 2-off neighbors and 3-off. So if you know what I'm talking about, great. So yeah, a stack would also be utilized for doing a DFS, a depth-first search, okay? But let's go ahead and jump into now the implementation here. So we've showed you guys that we need a add method, or an add function, a remove function. We probably want a function that returns the count, so how many values are in our stack. So maybe a get count, and then maybe a is empty or something like that, right? So let's go ahead and begin writing this. That way you guys have an idea for how this works. So first thing we're going to do, let's create that push function, right? So we have a stat class here. And say we want to create it, we're going to need some way to store our data, all right? So usually a stack or a queue are created with common structures that you guys have all used before. If you've used an array, that's one way to do it. If you've used a linked list, or you know what a linked list, that's another way to implement this. There are benefits to there are positive and negative aspects to using either of those structures. But those are very common ways to implement it. In C#, we have the list option, which is kind of like a dynamic array structure, kind of like a vector. The difference between, I think, the list and a dynamic array in C#, which I don't even know if there is a dynamic array readily available, is I believe lists do not happen to enter their information in contiguous space. So that's going to be a downside. Additionally, it takes up more memory than an array. So if you know your stack is going to be a fixed size, you can go ahead and allocate an array to it. If you know it's going to potentially grow continuously and it needs dynamic size, then you may want to use a list, especially if you're in C#. Easy stuff to implement, but it's up to you. In this case, in our example, I'm going to go ahead and use a list. It's really simple to utilize, so let's go ahead and do that. All right, so I'm going to go ahead and create a list, and I'm going to make it a list of events. I'm I'm going to say stack values is the name. And there we go. So what I'm going to do next is, and I'll make this public, just like the class itself. What I'm going to do next is I'm going to create my push function, all right? So my push function can be a public void. I really don't need to know that it was successful in entering or adding it to the stack. I'm going to assume in this case that it's always going to work as long as our data or the input we're giving the function is valid, in which case it should always work, okay? So let's call it push. We're going to receive an int val, and in here what we're going to do is we're going to go ahead and do a stack values, and we'll add it to our stack. So let's see. What I'm doing right here is I'm taking a look at what the add function or add method for the list does. So specifically with a list, if you use an add, it adds the object to the end of the list. Is that what we necessarily want to do? It's up to us on how we want to access our data. If we do it this way, then what you can imagine is, let's go ahead and show you guys an example of what's going to happen if we do this. And I'll do it right next to it. So I'm going to really quickly just write the code. So what we'll do is we'll add val. So this is a valid way to do it. It's just, it's up to you if this visualization or if doing it this way is going to be too complicated. You just have to adjust your code for it. So the other option is we do like an add front or insert at location 0 every time. And there's nothing wrong with doing that. But let's go ahead and take a look at what this is going to look like. So let's imagine our first example here, which we started with number 5. So we do a push 5. That's going to enter into the stack values list. All right. Now, because we know every time it enters a digit, it's going to add it to the end of the list. What's going to happen now is when we go to enter 8, it's going to be to the right of our data, right? Or it's going to technically be the next piece of data in our list. And if we accessed it from front to back, then it would behave more like a queue than a stack. So let's go ahead and continue this with this, and I'm going to show you what you need to do to account for this. You're just going to have to access the data in reverse. So this is our stack. We entered 5. It was the first digit. Now 8, we pushed number 8. That adds to the end of our stack at the time. Now 1 adds to the end after 8, 4, and then 13. Now, in order to retrieve our data in a stack-like way, we need to make sure we remove values from the end of our list in order to make sure we behave the way it's supposed to. So in order to do that, we need to set up our pop function so that it does it properly. So let's go ahead and take a look at that. Actually, I think this way is easier than doing it with an add front or an insert front because you can just remove everything from the end each time you have to pop something. So let's go ahead and do a public int pop. This will have no parameters because it's always going to remove the value that's on the top of your stack. But what it does, when you remove that, it's returning the value that was within that object, all right? Or it's removing the object itself if we're using like a custom object, right? So let me have a quick sip of my coffee. So simply, what do we need to do here? What we need to do is we need to remove the value at the end of our list object, right? So stack values, we're adding, every time we push a value onto it, we add it to the end of our list. So our list currently looks like this. Now to remove data from there, what we need to do is we need to, let's say, get int temp and get it from the end of our list. So let's say stack values dot, let's see, do we have something that'll get us the last digit? Let's take a look at what methods are available. We don't want to clear. So one way we could easily do this is we could just get the count, however many objects are in our list, and we can actually index, we can retrieve the value by index using a list, which is really nice. That's one of the really convenient aspects to this. The other option is it looks like they have a find last index. But let's see what this does. Searches for an element that matches the conditions defined by the specified predicate and returns a zero-based index on the last occurrence. Okay, so I don't necessarily want to do that. I think it's simpler for us just to get the count rather than doing any kind of searches. Getting last index seems to be doing like a search for a particular predicate or a particular search filter or parameter. So what we're going to do instead is we're going to first get the value at the last location of this list. So what we can do is we can actually access it using brackets like you can in an array. So it's going to allow us to dereference a particular index in this list. Lists are zero index, just like an array, so it should be really simple to translate between them. And what we're going to do is we're going to access stack values dot, what is it, count? Perfect. So because this is zero indexed, if you try to access stack values dot count, you're going to get a null reference error because you've gone past the last index by one. Imagine you have this this list here, right? It has 5 digits in it. When you do a count call, it's going to go ahead and do a call a getter, which is going to return to you 5. That last digit is not in the 5th index. It's in the 4th index because they're zero indexed structures, right? Like an array. So 0 index, 1 index, 2 index, 3 index, 4 index. So what you need to do is you have to make sure you go ahead and reduce that by 1, all right? So it's like a one-off error, all right? So this is going to get us the last digit in our structure. Great. Next, as it's written right now, there's 2 problems. One, we're not removing that last digit from our stack. So as it is right now, our stack value still contains it. All we did is we accessed it and we copied it into a temporary variable. All right. Next, we're not returning that variable yet. So first thing I want to do is before we return anything, I want to go ahead and remove that value from our stack. So to remove that, what we can do is we can say stack values dot remove, let's see, remove at. That should be fine. And what we're going to do is we're going to remove the last object. Just like we accessed it, we can just say stack values dot count minus 1. There we go. So this should remove the last digit every single time. If you want to go ahead and comment that, or if you think that needs a comment, you can, but I get what it means just by looking at it. You probably do too. Lastly, I said we need to return that value, so we want to return temp. Okay. So as this is, if we called pop, it's going to get a copy of that last value. It's going to remove that last value from our list or our stack. And then it's going to return that value that we removed from our stack. Perfect. That's exactly what we wanted. All right. Now, do you realize a potential issue with the code right now? So I'm going to give you a second to think about if there's an issue sitting in this right now. Okay, so if we were to have an empty stack, so imagine our stack has nothing in it, what would happen if we called this? So what would happen is we'd call this, we'd try to pop something off it, right here we'd try to go ahead and access something when our stack values count equals 0 minus 1. So it's going to try to access some -1 value. This will cause an error at runtime, and you do not want that to happen. So how do you account for that? Really easily, what you can do is you can make sure that your stack values dot count is greater than 0. Okay? So what you could do is you could really quickly add a little edge case check. If stack values dot count is greater, actually let's just say if it's less than or equal to 0, then return. All right. So In this case, it's going to go ahead and return -1 if that fails. Or what we can do is we can give it some kind of error return parameter or something like that. We can actually just do like a catch block too if we needed to, if we want to assume that we're always going to do this correctly. But in this case, what we're at least going to do is we're going to validate, okay, you're only ever going to return the correct number if you actually have values in our stack. What you could do is you could go ahead and actually make this like a flag parameter or something really far off, and you can always just account for the fact that that will return that particular output in the case that there is invalid input in there, or an invalid case. So that is one option. So how else, or what else do we need to implement? So we've got a pop, which should work. We've got a push. Now, a few other things that we said we would implement. We said we would implement a get count, all right? So a get count, all that's going to do is it's going to enable you to get the current count of values in your stack. So basically, if you were to set up your stack and use it, and you don't want to make this a publicly accessible list, which you don't want to, well, I'm telling you, you don't want to, then what you can do is you can create a public method for people to use in order to see how many objects exist in there. So if people say get count, what you can just do is return a simple stack values.count. Very simple, easy to use. All right. Lastly, I said we wanted an isEmpty, and actually there's one more we're going to want. It's the peek method, which is usually always available in a stack or queue type structure, okay? So an isEmpty. I'm actually not going to implement this. If you guys want to, it should be a really easy one for you. There's a few different ways you can do it. I'll let you guys get creative. What I'm going to show you guys, though, is the peek method, because I want to make sure we get that one in here. So we need some way to know what the value is of the object that's on the top of our stack. That way we can take a look at it if we want to before we remove data from it. So we don't have to, if we're in a case where we want to access it, we don't have to remove it and then add it back on, because that can cause some confusion, and developers can forget to go ahead and push a value back on in some cases, okay? So let's go ahead and recreate, or let's go ahead and create a peek method. So a peek method is going to get you the value of the object that sits on top of your stack. So how would we do that? Like our pop method, it's going to be very, very similar. We would do it in the exact same way with our little edge case check, but we're not going to remove anything from our stack. Because all we want to do is we want to provide the caller, whoever's using this method, with a way to see the value. We don't want to remove anything from our stack, okay? So it's as simple as taking the exact same thing we implemented in the pop and removing its actual removal from the stack, all right? So this is the implementation for a very, very rudimentary stack class for an int only, okay? Now, you can go ahead and change this. If you wanted to make it generic, you could. If you want to make it specific to whatever you're doing, go at it. All right, but what I want to show you guys is a quick implementation just to test this. So we want to make sure that this works, right? So let's go ahead and actually implement a quick test in our code here, just to double check that it's working as we mentioned, all right? So let's go ahead and create a stack. Okay, so I'm creating a stack, cool. And we'll just call it that is equal to new, perfect. All right, so at this point, we should be able to go ahead and push our values. So if we do a push 5, we can go ahead and just clone this. And let's go ahead and push the exact data we thought we were going to do here earlier. So 1, a 4, and a 13. So what we should see if we were to print this out after each statement or peek it is we should see that the top of our stack is this value, all right? If we wanted to print this out, we could remove it, and we'll see that when we print them all out, we should see our stack printed in reverse order from what we entered. So it should go in first. We're going to enter 5, 8, 1, 4, 13. But if we are going to print all of the stack out, it would print out 13, 4, 1, 8, 5. All right. So let's go ahead and actually do that. What I want to do is I want to go ahead and print out our entire stack. So what we could do is we can call our pop method and do a console.writeLine and do it within a loop where the loop is checking to see the current count of our stack on each iteration. All right. So what we could do is we could say while stack.getCount is greater than 0, what we want to do is we want to do a console.writeLine. Actually, we can do a console.write. Write line will look better. Let's go and do a write line for now. And what we could do is we could print out the pop, which is going to be an int, every time that runs. Okay, so what we should see in this, we should see 13, 4, 1, 8, 5. And what I'm going to do is I'm going to add a breakpoint to the end of my main function here, just to make sure our console window doesn't automatically close. And I'm going to go ahead and build this. We haven't built our code yet. Okay, so nothing failed. It all succeeded. And I'm going to go ahead and run it. So what I want to do is I want to run it without debugging and just see what happens. All right. Object reference not set to an instance of an object. Oh, okay, so I probably did not call new here, which means that it did not create an actual list object in my class. So I went ahead and did that because our class object does need to create this in memory. Oh, am I making a mistake? Do I have to add this to the constructor? I probably do. So let's go ahead and create a constructor here. So let's go ahead and say void stack. And we will initialize this here. There we go. So that should fix it. Let's just make sure I'm doing this correctly. Never assigned to and will always have its default values as null. Stack values. Let's see. We're adding. Okay, so that fixed it. I just had to recompile. My IntelliSense was not updating. So let's go and take another look here. Okay, so if you take a look at our code, we've already breakpointed. We printed out our code in the way that we expected. So looking at our main function here, let's take a look up here. We entered our data 5, 8, 1, 4, 3. And then we popped all of the data off the stack. So what we did was we printed 13 first, 4, 1, 8, and 5. So as you can tell, what ended up happening is we entered all of our data set into our stack, and when we removed it from that stack, it reversed the order of them. Okay? So really simple stuff. Now, before we kind of log off of this topic and we move on to queues, let's go ahead and really quickly show you guys what this would be like if you just used the collection.generic version, all right? So you don't actually go and create your own version where you'd have to create like a overload for every type of data type or create a generic type stack because it's already done for you. Okay, so let's go ahead and stop running and let's take a look at our main function here. So I'm going to leave this code here because I think it could be valuable for some of you guys to understand what's going on in the stack. And if you guys want to try it on your own and try something a little bit more challenging than using a list, the reason I use the list is because it's very simple. then what you could do is you could try implementing this with just an array. So if you implement it with an array and you define the size of that array, then what you're going to have to do is you're going to have to keep a, let's say, a reference to the top of your stack, okay? So when you remove data and add it, you're going to have to add it in a creative way so that you always know where the top is and where you always know where the end of it is. And what you could do is you could always keep that, you can always enter data from one side to the other and just keep a note on what index the top of your array is, and that's how you would do it. Okay, it's a little bit more complex. It's going to require a little bit of a tweak to the code, but I definitely recommend, if you haven't done this yourself, try it yourself. And if you get stuck, send me a message. It's really simple to debug this type of thing in C, C++, C#, Python, JavaScript. I could definitely help you guys out with that really quickly. So let's go ahead and show you guys this exact same code, but let's go ahead and use the collection generic version, okay? So if I wanted to do the same exact thing, I can go ahead and implement it using collection.generic. There we go. So how do we know that this is using collections.generic? If you scroll over it, you can see that it's coming from the system collection.generic stack class. So great, it's not coming from mine anymore. And very similarly, you're going to see that there's a push method. So let's go ahead and push the data we did earlier. So if I go ahead and just duplicate this, exactly like we did before, 4 and 13. And what I'm hoping for, and what is awesome for you guys, is they've implemented a ton of helper functions in here to make your life simple. I'm hoping they have a print all. Let's see. I don't see a print all, dang it. They don't have a print all, so we're still gonna have to loop it. Dang. So we're gonna do it exactly the same way that we did before. Really simple, but some cool things about this is take a look at what options they have. So you can actually reverse your stack. You can convert it to an array. You can convert it to a list. You can convert it to a dictionary. There's a whole bunch of ways to search it as well. So like I said before, if you wanted to access a value that's not at the top of your stack using one that you create yourself, you're going to have to create that functionality as a additional method within that class, right? So by using the generic library version, it's already implemented all those helpers for you. So it's great. Plus, there's no reason to recreate the wheel unless you're getting really custom, and maybe you're not allowed to use the libraries, or you don't want to use the libraries because it's going to bloat your software. Okay. In any case, let's just go ahead and show that this works. So while our stack.count is greater than 0, we're going to go ahead and do a console.write line of stack.pop. So remember, what does the pop do? It's going to go ahead and print out the, it's going to go ahead and return and remove the value that's on the top of your stack. So this should look exactly the same as our implementation. And what we should see is 13 on top, 4, 1, 8, and 5 below. Let's go and run this. Take a look. 13, 4, 1, 8, 5. It printed it in reverse. Perfect. It worked. Excellent. So let's go ahead and move on to queues. So what I'm going to do is I'm going to go ahead and implement our queue class right above our stack. All right. And I'll keep this here, and I'll just implement right above it. So let's go to make a public class queue. Nope. And this time, let's remember how a queue works. So a queue will always remove the thing that's been in there the longest. So it's first in, first out. So it's FIFO order, all right? Now, similar to a stack, we're going to need a way to add. Usually with a queue, you call that an on queue. All right, we're going to need a way to remove. Usually that's called a dec or a dequeue. We're going to also want a way to get the count. So we can do another get count. We could add a peek to this, and you may want an is empty or something like that. All right. So in this case, what I'm actually going to do is I'm going to use a linked list to implement this. Okay. And if you think about the way a linked list works, if you're talking about a single linked list, which contains like a pointer to a head and maybe a tail, then how would you solve this? Well, it depends. So if we're using a linked list, let's imagine that we're always adding nodes to the end of our linked list, even in a single linked list, because we contain a tail pointer every time. So if we're always adding to the end of our linked list, and we always remove from the front of our linked list, then we basically have a queuing system. Additionally, if you always do that in reverse, so if you always add to the end of your linked list, or to the front of your linked list, sorry, and you remove from the end, you have a queuing system as well. So let's go ahead and visualize that. So if we go ahead and run an example case, let's add the number 5 to our linked list. Now, let's play the case where we always add to the front of our linked list, okay? The next number we add is 6. So now the head pointer points to 6, and 6 points to 5. Now we add 13. Our head pointer points to 13. 13 points to 6. 6 points to 5. If we wanted this to behave like a queue, then what we would need to do is we'd have to remove from the end of our linked list every time. So this is an example of adding to front of linked list. Okay. Now, if we wanted to do it where we add to the end of our linked list, what we could do is add to end of LL. Then we have our head pointer. Let's go ahead and add our 5 in this case. And then we add our 6 and then our 13. In this case, all we do is we print or we remove our first object, which the head is pointing to, every time we want to dequeue or deck a value out of our queue. All right. So again, we're going to use a linked list for this. You could use an array or a list in C#. Either way works, but I want to give you guys an example of using a linked list here. So I'm going to use the linked list that's already created in the libraries, and we're going to do another example using ints. So I'm going to call this my queue. Within my constructor, I'll go ahead and initialize it, or instantiate it, is equal to a new queue, and it's an int form. Perfect. So now we've created our queue. Oh, linked list. Whoops. Little typo there. So now what we need to do is we need to go ahead and add our add method here. Okay. So what we want to do is we want to make a public void on queue. We'll take in an int value, and in order to add it to our list, what we need to do is we need to see what options the linked list class comes with. I have a feeling that it comes with a lot of really good options, so we could easily implement either one of these. I'm going to go ahead and implement the add to end of linked list. What I would love for you guys to do is I'd love for you guys to try out adding to the front on your own. Now, first, let's go ahead and start with the add method here. So if I wanted to add to my linked list and using the linked list class, and I can go ahead and do a queue dot, let's say I'm adding to the end, add last every single time. And what this will do is this will add a new node to the end of our linked list every time we call it. So that's exactly what we want to do in my case. Next, what I want to do is I want to remove. So I want to do a dequeue. So I want to be able to return the value when I remove it from the linked list, just in case I want to use it. And How do I do that? So let's take a look at what options the linked lists come with. Well, what I could do is I could always do a remove first, right? So if I always add a value to the end, then what I can do is I can always remove from the head of my linked list in order to make sure that I'm following the FIFO first in, first out ordering of a queue. So I call remove first. Perfect. Now, what we want to do is we want to make sure we store this into a temporary variable, just in case somebody wants to use it. Plus, we need to return it. And what we could do is we could do a return temp. So the last time we did this, let me just double check. Oh, okay. So this is good to know. If you do a remove first, it does not return our first value. That is great to know. This will just remove it from our actual linked list. So similar to our implementation with a list, there was a function, there was a method call we used to remove, but we stored our data before we did that. So we need to get our data first before we actually remove it. So let's do a queue, and what else can we use? Can we do a peek? Can we get front? Let's see. It looks like first is possibly what we're going to use. Gets the first node of the linked list. Add. Count. So we're going to use first. That's going to get us the linked list. That's great. And what we want to do is we want to get the value. So the reason I'm specifying value here is because you have to remember a linked list uses nodes. A node contains, depending on if it's a single, double, or other custom flavor of linked list, it contains a value section, and then it contains references to other nodes, okay? So we want to specify the value. Otherwise, if we just say q.first, that's just going to get us a node. You can see here that returns linked list node. So we're specifying value. That's going to get us the integer we're using. And then we're going to call remove first. It'll remove it from our queue. And then we return our value that we stored. Okay. So let's go ahead and think about this. If we were to call DQ without checking to see if it's empty first, what would happen? Well, unless the library has some sort of error checking already in it for us, I suspect what's going to end up happening is we're going to get a error at runtime, okay? So let's go ahead and do a check here as well. So if Q, do they have an empty? Let's see. Let's just say count is less than or equal to 0, then return some negative 9999999 value. Perfect. So we're just handling a potential error case. So let's go ahead and do our peek method next. How do we do our peek method? It's going to look very similar to our DQ, but we're not actually going to remove the data from our queue. Okay. So we're just going to remove that remove first call in there, and that means we're no longer going to actually remove it from our queue structure. All right. So make sure we call this peek, and let's go ahead and add our comment there. Lastly, we have the get count method here, so we can go ahead and do a public int get count, and you guys saw that I was able to do a q.count here. All we have to do is return this q.count, and we've got a get count function that people can use, okay? So we've implemented our queue class now. We've created a queue on queue. The queue is the constructor. Bleh. We've created an on queue, which allows you to add values or objects onto our queue. A dequeue or deck, which allows us to go ahead and remove objects from our queue. A peek, which allows you to take a look at the value in the object at the front of your queue. And a get count. Again, this is probably the most simple implementation that you're ever going to use. You probably will very rarely implement this yourself, but it's a good thing to practice. Again, if you guys want to implement this on your own with an array, it may be a fun challenge for you to do. You're going to have to keep track of where your queue basically front and back are, if depending on how you implement it. I think you guys should try to test doing this yourself, but using the method I mentioned in the beginning here, where you add to the front of the linked list instead of adding to the end of the linked list, and see what you need to change to make that work. Now, before we go ahead and sign out here, I want to show you guys that this works. Okay, so we tested our stack here. I'm going to remove this test case, or I'm just going to comment it out. Removed. All right, and then I'm going to go ahead and create a queue using our version is equal to a new queue. Perfect. And I'm going to go ahead and queue up some numbers. So I'm going to on queue maybe a 5 and then a handful of others. All right, so like a 1, a 51, a negative 12, and a 15. Lastly, what I'm going to do is I'm going to print this queue out. So what I want to do is I'm going to do similar to how we printed our stack. I'm going to loop through until our count is equal to 0, and I'm going to dequeue or deck every time we do that. And the way I'm going to do that is I'm going to do a queue.getCount, and while that is greater than 0, we will continue to console.writeLine. What we should see is we should see this print out in order each time. So we'll do a dequeue here. And we're probably getting an issue here because this is a method call or a function call, and that's what it's going to say. So let's let this error come back. Yep, operator greater than can't be applied to operands of method group. So it's on some method, so you're going to go ahead and add that, and that will work. So what we should see print out is a 5, 1, 51, negative 12, and 15. So let's go ahead and fact check that. Let's see if that's true. So I just ran it. If we take a look at our output here, blow that up and zoom it in so you guys can check it out. So we have a 5, 1, 51, negative 12, and 15. Perfect. So our queue worked. Now let's go ahead and just really quickly modify our main function with the system.collections.generic version of the queue. That should be really easy. So I'm just going to go ahead and modify this so that it uses theirs instead of mine. So there we go. Now the queue is calling the systems.collections.generic queue. You can confirm that because it's referencing its class. If I scroll over the class here, or the class declaration, they use the exact same on queue call that I do. The difference that they're going to have is they're probably using a getter to allow us to access the count. Yep, so you can see that's an accessor. So that's perfect. That works just the same. Just had to make a slight tweak there. It's not a method call. And we're going to go ahead and print it out exactly the same way. Their implementation also uses a dequeue, which we would assume. So we can confirm that going to hit F12. This is their actual implementation here. And if we run this, then we will see the exact same output we just did. So let's go ahead and start without debugging. And you can see 5, 1, 51, negative 12, and 15. Perfect. So both methods worked. So let's go ahead and end off there. So what we've done so far is we've implemented a stack and a queue. Both are very useful data structures to understand and know how to utilize. There are different use cases we're going to use them. If you want to retain the ordering of your data set, then you're probably going to use a queuing structure. If you want to reverse the order of your data set, you'd use a stack. Why is that? Because a stack is a last in, first out structure, while a queue is a first in, first out structure. If you're doing something like a DepthFirst search with a graph or a map, right, or trying to find like the nearest neighbor type problem, and you want to do a depth first search, you'd use a stack. If you want to do a breadth first search, you'd do a queue. Okay. If you're curious as to why that is, I really do encourage you to take a look into graphs and graph searching, because those are the way you do it. That is it. Okay? And if you're ever going to implement those searches on your own, or if you're trying to pass a coding interview and they ask those questions, a lot of times they're going to need you to explain how this works. You may not have to write a queue from scratch or a stack from scratch, but you're going to have to know how they work. So it's good to have a solid understanding of what's underneath the hood, so that you can speak about it if you're asked about it. Okay. Now there are some time complexity things that you may want to know about this. For example, in our queue we used a linked list underneath the hood. So you could think about what the repercussions are going to be with that, but you'd want to also know what kind of linked list we used or how we used it in our case. Okay. Same thing with the stack. In most cases, with both of these structures, to search for an object, you're looking at a big O of n time complexity, okay? The reason being is you are always accessing data in the same way. You're either popping off the top until you get to the value you want, which could always take the entire n values. Same thing with a queue. You're always dequeuing from the front of your queue. So that can always be a big O of n computation. All right. Now, to add objects to your queue or stack is very fast. You're looking at a constant 1 implementation there. Of course, there could be complexity underneath the hood if you're using like an array and it needs to dynamically resize because you've hit the maximum size. And that's a different story from what the actual structure does. So the bottlenecks there are a little bit different, and analyzing those time complexities is going to depend on your implementation. But you can imagine that anytime you add, it's going to be a constant 1. And anytime you do a search, it's technically a big O of n. Anytime you do a removal, it's technically going to be a big O, a constant speed. It's just going to be a 1. Because you always dequeue from the front, you pop from the top. Okay? If you're trying to remove a specific value, then you've got a big O of n. All right? So that talks about a little bit about the time complexities. You can really analyze that yourself if you take a look at the code and you understand the way you implemented it. And that is why it's valuable to have implemented this from scratch on your own, okay? Because then you understand how it's been made, how the data manipulates within the structures, and how the pointers work to keep track of what the front and the end of the lists are, or the front and end of a stack or queue are. So I hope this was advantageous to you guys. This turned into a longer video. I am not going to split this up. I'm going to make this as one longer video for you guys. And I'll try to add some timestamps throughout it to mark where the differentiation between stack and queues are. This is Eastwood Journey to Programming. If you magically made it this far, please do subscribe. We do appreciate it. And have a good one. I will definitely try to make a DFS and DepthFirst Search tutorial in the coming future. Have a good one, guys.